Aha. All right. Yeah, so I should probably start by thanking the incredibly supportive community. I literally could not do this without you. And of course, a big thanks to my computer again. So I've been at Facebook for a little over a year, and I've been very fortunate to be able to work with Jordan on a lot of these things. So mostly I've been working on the Reason Native project that Jordan alluded to, and specifically I've spent a lot of time working on the testing framework Rely. Now, I certainly understand that a lot of you might not have direct experience with native development, so I decided to make this talk a little bit more theoretical and talk about the basic principles behind why we test. So while the examples here will be using Reason and Rely specifically, the principles I'll be talking about here extend beyond any particular language or framework. So really what we want to understand here is why we write tests, and from that understanding I want you to have the ability to write code that you're a lot more confident in and can better serve your needs. We're going to go into a few kind of specific strategies that I think Reason is well suited to, but as I said, that nothing here is specific to Reason. So I think it helps to start with the basic fundamental question, why do we test? And I believe the answer to this is because we want to be confident that our code does what it says it does. As Jordan said, the most important person in this equation is the user. And we're trying to solve some problem for the user, and if our solution doesn't actually solve that problem, then the user is going to look elsewhere, for those solutions. Now, the confidence that we're after, I don't think there's any reason necessarily that it has to come from testing. Like computer science, software engineering, like these things are based on mathematics. And in mathematics, we have this notion of formal proof. If you want to show something is true, you have some set of axioms and rules for logically combining them, and you have this derivation, which is this proof that shows why your statement is true. This gives you a form of absolute confidence that can be very valuable. Now, we program using programming languages, and the language semantics have some properties that you can prove things about, and you have type systems. In a lot of ways, a compiler is a program that is doing some automatic proof generation for you. So if we're able to leverage the compiler and the language, we're able to get similar confidence levels that we would be able to get using these formal mathematical proofs. However, we actually end up writing a lot of tests. And tests offer something that is very different. And I think that it's important to understand the difference. With a mathematical theorem, you have some proposition that you're saying is true across, for all the natural numbers, or something that is very well quantified. But when you're doing a test, you're only showing that a specific instance of a more general proposition is true. And I think that this distinction is very important, and is kind of what Dijkstra is alluding to here. So I'm going to go through an example with you. So you might be familiar with the factorial function from some point in math class, maybe in college or high school or something like that, and it's defined in the following way. So 0 factorial, which is this exclamation mark, is equal to 1, and n factorial is defined to be equal to n times n minus 1 factorial. Now, this structure lends itself really easily to a recursive implementation, which I've created here. And because I have to show this to you guys, I want to be pretty confident that it's correct. So I actually wrote a formal proof for it, and this is just using mathematical induction and substitution essentially to show that my proposition holds. We're not going to go too deep into this, but I think the key observation here is that this is very closely tied to the actual source code that I was doing. I'm applying substitution and showing that some invariants are holding. And if I were to change this code later, I would have to adjust my proof accordingly. Now, there's a very strong temptation to say, oh, if it just compiles, it works. And I find that in the functional community, there's a little bit of a tendency to write fewer tests than you might otherwise. And out of the box, the Reason compiler isn't really saying much more other than factorial is a function that takes an integer and it returns an integer. We also have this weird behavior where you can throw an exception in some cases, and that's not really reflected in the type signature at all. So really what it's saying here is, factorial is a function that takes an integer, and if it returns an integer. Now, in actual practice, this is something that we might actually expect to see. So this is just a test suite I wrote using Rely. The syntax here is very much inspired by Jest, and hopefully you're able to follow along. But basically, we're just showing kind of some basic cases. There are base case holds, factorial 1 works, and then we kind of picked an arbitrary value and even tested an edge case here. Now, in the previous 2 examples, we have, the proof shows that for all natural numbers n factorial is equal to factorial n. The type system said, if this function returns, it's going to return an integer. This is only saying that, for these 4 particular values, we have this behavior. And we write this test with the faith that, the developer, which is, probably ourselves, but it could be someone else, is going to do a good faith effort, and that this is like a reasonable approximation of the truth of the theorem, and they're not going to actually write something like this. And that's kind of reasonable generally, but, there is a difference in certainty there. So now we've talked about this difference in certainty. I think the question is, well, why don't we just prove everything? And I already alluded a little bit to the answer, and the answer really is cost. So it takes, time and skill and effort to actually write these proofs and verify them. And additionally, in a lot of cases, they're these manual proofs are highly dependent on the source code itself, which can lead to pretty severe maintenance headaches when you have to modify the source code. However, formal proofs are used in a lot of environments. So in academic research, security analysis, and some embedded systems environments, formal proofs are actually utilized. And like I said, type systems are kind of formal proof checkers themselves. In theoretical mathematics, computer-assisted proofs have been used since the 70s. There's this thing called the 4-color theorem that was first proved using some computer systems, and there have been some advances there as well. And when researching this talk, I actually found an interesting library called Coq, spelled C-O-Q, that's actually made by INRIA, which is the same French academy that created and maintains a camel. If you're interested in learning more about automated proof techniques, I think this is something that's pretty cool to check out. I could definitely see kind of a place where automated proof verification and authorship eventually starts to take a greater role in kind of common software development practices. So onto our type system. What if our types actually enforced our business logic? The idea of if it compiles, it works is really powerful. And I just spent all this time talking about how great it would be if we had automatic proof verification. And it turns out that for a non-trivial number of requirements, you can actually design using types and encode your business logic constraints in your types and get a greater amount of certainty than you'd be able to get with tests alone. I've prepared for a couple examples for you using this. There's certainly a lot more that we can go into, and I encourage you to explore this topic on your own as well. But for this first example, money is a very common thing that you're modeling in your applications. And you have these rules about money, specifically that you can't add 2 things of different currency together, right? So if you have a price that is in euros, you shouldn't be able to pay in dollars. And a lot of the times that you do this, if you're thinking like a standard object-oriented model, you'd have this money object, you'd have a currency, you'd have an amount, and in the functions that add them together, you do this verification on preconditions that the currencies match, and you'd have some tests for that. However, the tests themselves are only ever showing exactly what the test cases prove, and if you don't have these tests, you're at risk. By modeling types in this way, we are actually making it a compile time error, so we're making it semantically impossible to make these types of errors. For a real-world example, Rely has these lifecycle methods, basically before each and after all and things like that, so you can perform test setup data. And we want to make it concurrency safe, so we're returning values from these things and passing them to each other in the tests within them. And as a result of that, we have these requirements that they need to be called in a certain order. So specifically, before each can't be called after each. And in order to enforce these requirements, we're actually keeping track of whether or not these functions were called using something called phantom types, which again is something kind of interesting to Google if you're interested in going down that rabbit hole. And the kind of end result is, if you call things in the wrong order, we actually have a type error. If I were to actually write a test suite for this set of things, there's just a lot of cases to cover, and I probably wouldn't have been able to do it exhaustively. And there's a lot of edge cases. But by encoding these requirements in the types alone, we're able to have a greater degree of confidence and a greater degree of coverage than we could have accomplished with tests alone. Designing with variance in general is also a technique that can help reduce these types of things by making invalid states impossible to write via your type system. You're ensuring a greater level of security. So we still do actually end up writing a lot of tests in practice. And I think the reason for this is that software is soft and it is constantly changing, and the requirements that we're dealing with can't always be encoded with the type system. Tests allow us to depend on higher level abstractions than proofs can, and they're a lot easier to write and run automatically currently. Encoding our constraints in types is very valuable when we can do it, but representing things like a function, just like a function that doubles its input in types, is extremely difficult. You can represent the natural numbers in the Hindley-Milner type system, but it's not the most practical in most cases. So tests are kind of what we actually have. But I think it's important to understand the caveats that come with them and understand how we can get use types when we can, but understand where we actually need them. And testing as a subject is incredibly broad, right? You have unit tests, integration tests, end-to-end tests, performance tests, manual tests, all of these different things. And they all have kind of different costs and values, and depending on what you're doing specifically, the relative value of them can change pretty rapidly. That's why this talk is called Investing in Testing. I think it's important to understand some of the fundamental principles behind where this value comes from and how to apply it. And I think it's helpful to start with kind of our shared context. So how many of you have seen something like this before? Yeah, so that's most of the hands in the room. And this is the testing pyramid. It's a heuristic that was introduced by Mike Cohn in around 2009, I believe. And this is, I think, when you talk about testing theory, one of the first things that comes to mind for many people. And there are, I think, some very useful things here. So I think the most immediate takeaway for me is that the optimal strategy is some kind of mixed strategy. Which is to say that you're not just writing all unit tests or all integration tests or all end-to-end tests. Some kind of mix is the best. And I think if we think about this intuitively, it kind of makes sense. So if we had a bicycle or something that we wanted to test, we can imagine we had a unit test for the wheels, a unit test for the chains, the brakes, the bell and stuff like that. But if you didn't actually write it down the street, you're not actually addressing the user's use case. So that first end-to-end test also offers a lot of value. At the same time, just writing a test the bike down the street won't necessarily tell you that the wheels hold enough pressure, right? Because you're not getting enough stress on that particular component. So some kind of balance between direct use cases that you're actually trying to solve the problems for and quality assurance to make sure that you get the tricky parts right is important. And when this was originally presented, the idea was that as you go up the testing pyramid, the tests become harder to write and they become slower to run. And these are assumptions about cost essentially. And in the history of software development and computer science, costs have dramatically reduced over time, right? So I'm sure you're familiar with Moore's law, and a lot of the recent rise in functional programming can probably be somewhat attributed to the cheapening of memory and the desire to have stable abstractions for doing concurrency safe operations and utilizing multiple cores. So the problem with these assumptions, like I said, is that they don't always hold. So a user on Discord recently posted they were working on a native HTTP server, and he was working on writing some end-to-end tests, and he said that, I have this test that runs in 3 milliseconds, and it spins up a server, makes a request, and verifies that it was actually sent. My first reaction was to help him verify that this test was actually running properly, because I didn't believe this. But it really was. And when your end-to-end tests are running this fast, your strategy should probably no longer look like a pyramid. Because, like I said, we really care about what the user is doing, and when you have this type of performance, you're able to more rigorously address their use cases directly. Now, I've just spent a bunch of time talking about how great integration tests are, and we're all talking about building confidence for the user. What becomes the role of unit tests then if you don't have to rely on them due to performance considerations necessarily? And I think they make sense really for the tricky parts, for kind of lack of a better term. If there's some complex logic going around, I think it's a good idea to actually write these unit tests. But generally speaking, if I'm confident in what I'm doing, I'm going to skip it. And I find that writing in a functional style makes it a lot easier to do this. Not using a lot of for loops and if statements, just having list.map and programming via functional composition and the use of pattern matching makes it so that I'm more confident in what I'm writing. And generally speaking, if I'd be writing for the tests for these things, the test would look a lot like the code itself, which isn't the best thing. The common counter argument I hear for something like this is that your code coverage must be terrible, and I don't think that code coverage is necessarily a useful metric, and I don't think that the code coverage will necessarily be bad either. Rely has nearly 100% code coverage, and it's very hard to actually measure because I'm using Rely to test Rely to measure code coverage, so that doesn't work super well. But the general idea there is that, so imagine the bicycle example again. I might not write a test for my chain for some reason, but if I'm riding the bicycle down the street, the code that is actually turning the chain is still going to be hit. So what I think the useful metric to strike for is use case coverage. If there is some requirement that you could verbalize to a user, if it's not encoded in your types or in a test, then that is a problem. And that is what you should be striving for. The kind of opposite isn't necessarily true. If you have very high code coverage, your use case coverage could still be very poor. You can imagine you have all these unit tests for the bicycle, but you never actually wrote it down the street, and as soon as you start it, it starts to move, the wheels don't turn or something like that. Now, we've talked about these foundations using a strong static type system and a focus on integration tests and these things that matter. Some of you might have seen this before, but this is a little more recent. This is the testing trophy, which was introduced by Kent C. Dodds in his 2018 talk at, I think, Assert.js entitled Write Tests, Write Tests, Not Too Many, Mostly Integration, which was based on a 2016 quote by Guillermo Rauch. And really, I think this incorporates a lot of the ideas that I've talked about here, which is that we want to have a very strong static type system because these give you more confidence than anything else. And then aside from that, the integration tests are what we actually care about in terms of our users. It's also a lot less prescriptive in terms of the rough distribution. The pyramid has a very clear hierarchy, but here the relative sizes of things are a little less clear. And I think that's very important because if you're writing a native Reason application, you can write a ton of integration and intent tests, but if you're still running in a browser environment, you still might have some constraints, or if you're not writing Reason at all, you could still have these considerations where your integration and intent tests can be slower. But I think it really does a good job of communicating some of these ideas. But the heuristics we've looked at are just that, really, heuristics. And I think it's helpful to start by looking at the fundamental things that I think make tests valuable and make tests costly, and talk about some ways to enhance the benefits and minimize the costs, and while roughly mapping these things to common types of tests that you might see. So in general, I think that the characteristics of valuable tests can fall into a few buckets, and not all valuable tests will fare well in all of these attributes. So I think the most important thing has to be relevance. If you take away one thing from this, it's that we write software to solve problems for users, and that we care about getting our behavior right for the users. So by encoding our requirements and tests, we're making sure that users are able to make the software as intended, and we're also making our software more resilient to changes in implementation details. Users care about high-level behavior, not implementation details. As we add new behavior requirements, the old behavior requirements are less prone to changing than the implementation details are. Obviously integration and intent tests will fare quite well by these metrics. By this metric, and unit tests will fail a bit more poorly. However, I don't think relevance goes beyond, I think relevance goes beyond just the requirements as the users see them, but can also extend to kind of the fundamental abstractions that are in your problem domain. So I think that identifying these abstractions and writing test cases against them themselves is also a very valuable thing. And the reason for that is it can reduce the cost of incremental development and really hone your understanding of the problem domain. So if we had some kind of like payment processing app, a payment method is probably an abstraction that you're dealing with, and you can model that and test against that using like functors or pure functions or like abstract classes depending on like the actual class that you're using. And then as you have individual instances of that, your tests can be as simple as this. This is an idea that I go a little bit more deeply into in a Medium article that I wrote called, there we go, called Testing Abstract Data Types with Reason and Rely. An abstract data type is basically a, this abstract kind of type along with some rules that we want to be true about it. And you can basically encode these rules as your test cases. And your abstract data type would be like the input would be some kind of interface or module type that would be going into your function. And then we have diagnostic value. So we have these tests, and the tests are there to preserve the behavior that the users actually care about, but it's developers who are actually maintaining them. When tests fail, it's important that you're able to rapidly diagnose the source of the problem and be able to address this. In general, this is something that unit tests do really well because ideally they're highly focused on a particular module of code and on a single point of behavior. And integration and end-to-end tests can fare a little more poorly by this metric because there are multiple potential points of failures. In general, when you have very cheap end-to-end tests, I think it can be helpful to have sometimes, the whole happy flow path, but also breaking that down into more individual components so you can better isolate failure and ensuring that you have unit tests for the actual complex points of the system. So hopefully there is a corresponding unit test failure when there is an integration or end-to-end test failure. Generally, focusing on testing one thing per test case is the biggest thing that will yield these main diagnostic value dividends. And then tests are really useless if they're not run, right? So it's really important that you run them often and that they be able to run relatively quickly. The faster your feedback loop is, the more effectively you can write software. The reason we're running our tests natively at Facebook for the ads work that Jordan, Kyle, and I are doing is that it's just much faster. We're running, right now, I think it's on around 5,000 tests in about a second, something like that. Less than a second, whereas running that with just, the first run will take on the order of 15 seconds and subsequent runs are still around 3 to 7 seconds. And Rely isn't even optimizing for only running tests on things that changed at the moment. So just being able to run these things more often is very valuable. In general, I think just having an idea of how fast each type of test takes to run in your application is useful. And sometimes, if you have longer running performance tests or longer running integration tests, it can make sense to run those as, separately from the rest of your tests, but ensure that they still run at some cadence. I find just having a set of tests that I can run locally and iterate on really just speeds up my development process. There's a lot of great tools out there for test automation. Azure, Circle, Travis, Jenkins are all out there. You should pick one and use it. We've talked all about wanting to have this confidence, and if we have this test suite, we need something that actually enforces that all the tests are passing for our code, or we aren't actually confident that our code meets the specification. You want it to run on really everything. And if you're not doing this, you're really missing the point. Right, so we've talked about some of the things that add value, and now I want to get into things that can, take away value or are just kind of the realities that we have to deal with when we're actually writing tests. So robustness and maintainability can be a little difficult to distinguish between but for me, robustness really just means resilience to change. And to illustrate that point, I'd ask how many of you have added a new feature and had a bunch of tests either fail due to not compiling or basically a false positive or a type 1 error? Yeah, half the room or more, and the rest of you are lying, I'm sure. So it slows you down a lot if you have to update a bunch of test files whenever you write new code. And in my experience, the best way to avoid this is kind of just looking at basic software design patterns. The object-oriented community has a lot of great things on this. The classic Gang of Four book on design patterns, clean code, clean architecture. These principles and patterns apply here too, right? I think that Jordan talked about saying that this is just like a declarative interface. Immutability is really the key add of functional programming, and a lot of the ideas about like working with abstractions and things like that that you might have learned elsewhere are still entirely valid. And I think one pattern in particular that's worth calling out is the builder pattern. So in my career, when I have the problem if I add a new feature and something doesn't work, most of the time it's because there is some kind of type. So here we have a user type, and we're manually constructing it, either via like populating the record fields ourselves, which is probably the most common source in like TypeScript or Reason, or using like a constructor if you're doing like Java or C# or Go or whatever. And then you decide to add a new field to this. So say we have our we wanted to add is logged in, and we do that, and we have 100 tests like this that are like, oh, now you need to specify is logged in. If we had been using the builder pattern, which is basically you have this object there where you can create a object in the mathematical sense and not necessarily the literal sense, where it provides some reasonable default values, and you can set the ones that you actually care about for your test case. If I had 100 tests like this, none of them would fail. We would just have a single point of failure in the builder, and then once we add a default implementation for these things, then our test would be good to go. So that is probably the biggest thing I've seen in terms of just minimizing this type of error. And here we've fixed the builder and our hundreds of theoretical tests. And maintainability I think of as when we actually do have a failure on our hands, or when there's actually a change in behavior and we need to be able to change the test, how able are we to do this? And this comes down a lot to just pure complexity. If you have huge setup steps and operations, it can be very difficult to write your tests. There's a lot of great UI testing frameworks now that can simplify a lot of things, and just having these these builders for the common domain objects in your application can really reduce your code complexity. In general, if you have cyclomatic complexity, which is just the number of linearly independent paths through your code, which you can shortcut as the number of if statements in your tests, if that number is bigger than 1, then you're probably doing a little too much. I think that the AAA pattern, which we see here, the arrange, act, assert pattern, is incredibly useful for adhering to this principle, and can also let you kind of understand that, okay, if I have a bunch of complexity happening in my arrange method, you can extract this either to common setup for your test suite, or to some common builder objects, and that can really increase the maintainability. And then finally, there's just the actual upfront investment. So writing tests takes time, right? If you spend a little bit more time on upfront design, you can possibly utilize types to reduce the amount of tests that you can write, and identify behaviors that you actually need to test. If your code base is lacking in test utilities, your upfront investment is a lot higher than if you'd spent the time to build your test builders and common mocking patterns and things like that. Taking some time to ensure that the side effects are pushed to the edges of your application can make it easier to mock your code when you test it. If you are utilizing mocks, you still want to make sure that you're writing tests against your actual production dependencies. But generally, just a lot of time down the road can be saved by a little bit of time upfront investing in understanding the core abstractions that you're dealing with and modeling your data effectively. If you're interested in learning more about Rely or any of the Reason native libraries, you can check them out at reasonnative.com. I'm on Twitter at the Banderson. I tweet a little bit about testing topics, and I'll be writing more about that. The slides that I used here, as well as the source code for these examples, are available on my GitHub. Thank you all very much for coming, and you can find me afterwards if you have questions.